So, good evening, everyone. Welcome to the 11th problem solving session for the course Environmental Remediation of Contaminated Sites. So, we'll wait for a couple of minutes and then we'll start. So, good evening. Welcome to the 11th problem solving session for the course Environmental Remediation of Contaminated Site. So, the course instructor is Professor Bhanu Prakash Velanki from IIT Roorkee. And I am one of the TA for this course. My name is Asma Parveen and I am a PhD scholar in IIT Kanpur. So we have completed till week 10. So this course was started with introduction about the hazardous waste and the rules in India associated with the hazardous waste management. That is the hazardous waste transboundary movement and management 2016 rules. And then we have also seen some other rules related to the management of waste, like we have seen the rule related to the management of solid waste, that is municipal solid waste management 2016. And then we have also seen a very brief introduction about the rules for management of medical waste, that is biomedical waste, waste management 2016 rules, and so on. And then in week two, we have also again we have discussed about in detail about the hazardous waste management rules, and then we have started to learn about risk for to find out the risk for carcinogenic and non-carcinogenic pollutants, in which we have seen that two types of problem related to depending upon the type of the pollutant. So for non-carcinogenic pollutant, we generally find hazard index which if it is greater than 1, then it shows the potential hazard from the pollutant, and if it is less than 1, then hazard is not that much. And then we have for find out for now carcinogenic compounds, where The exposure time is taken for the entire life duration, and we have find out the risk related to the different carcinogenic compounds. And if we have seen that if the risk is more than 1 in a million, then that risk is then that pollutant or contaminant is considered to be causing uh, cancers to cancers to a large population. And if the risk is less than 1 in a million, then that pollutant is not that much hazardous at that given dosage and exposure duration and time. And then we have moved to the different methods for remediation of the contaminated sites. So where we have seen the first method was the pump and treat method, where pumping of the groundwater is done and the water is treated on the surface ground on the earth's surface by pumping the contaminated water. So where we have seen an example related to chromium, that if the water is contaminated with chromium 6, then that water was pumped, and on the ground surface that was reduced to chromium 3. And chromium 3 generally exists in solid state, or it is or in precipitated form. So through this we can remove the chromium 6 by precipitating it into chromium 3. And also we know that chromium 6 is carcinogenic. On the other hand, chromium 3 is not carcinogenic. And also, we have seen that when the pollutant is only in the aqueous phase, then pump and treat method can be applied. But if the pollutant is partitioned, or if it is adsorbed or sorbed on the soil or sediments, and if it is in equilibrium with the aqueous phase, then the time required to pump the water and treat it is very, very long as compared to when it is in only in aqueous phase. So for this we have find out the retardation factor, which further increases when there is some NaPl in the sediments. So based on these, we have seen that pump and treat method is not efficient where there are where the pollutant or contaminant is soaked on the soil or sediments and is in equilibrium with water, and also when there is some other NaPl, that is non-aqueous phase liquid, present in the pores. So based on these, we have discussed for further move to different methods. So also we have seen that pump and treat is not from the retardation factor. We have seen that the time required to remediate the sites when there is contaminate soil between soil and in dissolved form in the water, then the time required to remediate increases, and it further increases when there is some NaPl phase in the sediment. So we move to the next method, which was the permeable reactive barrier. So in permeable reactive barrier, so these are the barriers which are installed directly into the aquifers, and the groundwater, while flowing through these barriers, so the contaminants are removed, or either they are sorbed or they are oxidized or reduced by the compounds present in the barriers, and the clean water flows out from these. So we have seen case studies based on these permeable reactive barrier also, where I think zero valent iron was used to remediate a contaminated site. And then we have also seen examples where we were supposed to design the permeable reactive barrier in which thickness of the PRB was designed. And then we move to the next method, which was the natural attenuation. So natural attenuation, it is the if there are some microbes present in the, so microbes are present everywhere in the environment. So if there is some microbe present in the groundwater, then it can also slowly uh, convert or remediate the pollutant present in the aquifer. So it can be constructive or non-constructive. So destructive and non-destructive. So based on the mechanism involved, so if the compound is getting immobilized, and if the original phase original structure of the compound is not getting changed, then it is non-destructive. But if it is getting degraded by the microbes into some other form, then it is the destructive remediation. So then we have also seen that we can enhance the natural attenuation by addition of uh, some enzymes, or by addition of some electron donors. And also we have seen that if we want a particular contaminant to act as an electron donor or acceptor, then all the higher electron donor and acceptors which give higher energy as compared to that pollutant should be removed from the aquifer, or they or based on the properties of the aquifer we will select the type of remediation to be taken, to be adopted. And then we have to the next then we move to the next remediation, so where we have discussed about solidification and stabilization. So, in solidification and stabilization, we have seen that the aim is to reduce the mobility of the contaminants in which some form of binders are added. So the pollutants, they are binded in some form of bricks or blocks, and and the mobility of the mobility or leachability of the contaminants are reduced. So the mobility and leachability was is checked by the TCLP test, that is a toxicity characteristic leaching procedure test, which is given by U.S. Environmental Protection Agency. So based on this method, the waste is so since we're dealing with hazardous waste, so the solid waste is taken, and the extractant solution is taken in the ratio of 1 is to 20, and then they are rotated at around 30 rpm for nearly 18 to 20 hours, and after that the concentration of the contaminant is find out in the filtered leachate or the filtered supernatant, and in that we find out how much portion of the contaminants is leaching out. So the main aim of the solidification and stabilization is to reduce the leachability of the contaminants and pass the TCLP test, because if the TCLP test is passed, then it means that the concentration of the leachable contaminants is below the permissible, below the maximum limit given by TCLP, and it can be a non-hazardous waste. But if if the limits for the various pollutant crosses the TCLP test, then that pollutant is or that waste is considered as hazardous, and all the treatment and disposal of that waste should be done according to the hazardous waste management rules. So, and then after solidification and stabilization, chemical treatment was discussed, in which we have seen that we can add some type of chemicals to enhance the remediation, in which we can add some electron acceptors or donors. So, in which we can add some chemical compounds that enhances the remediation of the site. And then we have the next remediation, which is the bioremediation, and then remediation for the soil vapor phase. So till now, all the methods which we have discussed is for the remediation of the contaminants, either it is in aqueous phase or it is associated with the soil particles, that is it can be associated with the soil particles or with the NPL. But in week 11 we will see the questions and concept based on the treatment and extraction and treatment of the contaminated vapor phase in the soil and sediments. So, there are, I think there was first two lectures were based on soil and soil vapor remediation, followed by lectures based on, I think next two lectures were based on bioremediation. So in bioremediation, microbes are degrade the pollutants into some safe or lesser toxic form, and then the last three lectures are on case studies for where bioremediation and soil vapor phase treatment has been done. Just give me a minute. Also, there was a numerical based on soil vapor phase. So we will try to solve a similar numerical in this problem solving session. And then okay. So So let me directly share my screen so that we can start solving the questions. So please go through the lecture videos for the for all the theory and concepts. So first let me share my screen. So bioventing and heat treatments. So these are the methods which are used to enhance the solid vapor extraction process. So in bioventing, what happens that oxygen and nutrients are supplied in the aquifers to enhance the remediation or the microbial activity taking place in the aquifer to enhance the conversion of the contaminants into vapor phase. So there are indigenous microbes present in the aquifers or soil sediments. So the degradation or degradation of the contaminants takes place through that. But if you want to enhance the increase the rate of the remediation, then oxygen along with some nutrients based on the type of the microbes are given are supplied into the aquifers, which enhances the soil vapor extraction process, so that the pollutant gets through microbial activity, they gets converted in more into the vapor phase, and then they are extracted and treated. And next is the heat treatment. So in heat treatment, so they heat treatment, the name suggests that there is some heating done in the aquifers, or temperature rise is done. So with increase in temperature, the vaporization of the contaminants will increase. So we know that with if the temperature will be high, then vaporization in rate increases. So with the heat treatment, the vaporization of the contaminants will increase, and which will increase their mobility from the soil or sediment phase into the vapor phase, and they can be easily extracted using the extraction wells or vacuum pumps. So these two methods, that is by bioventing and heat treatment, both these enhances the soil vapor extraction process. So statement is correct. So A is the correct answer. So now let's move to the next question. So the question is, consider the AFCO Lycoming Superfund site remediation case study. Which of the following statements are accurate about the methods and outcomes of the remediation process at this site? A. Molasses was utilized as an electron donor, not an electron acceptor. B. A consistent decrease in DC concentration were observed throughout the remediation. C. The site was polluted with TC, DC, BC, and hexavalent chromium. And the last option is post molasses injection reducing condition, not oxidizing, were predominant at the site. So, based on this case study, we have to say out of the following four, which one is the correct option. So, again, I'll give you all 3 minutes. Just take your time and write the option in the chat box. So the answer for question one is that the statement is correct, because both bioventing and heat treatment, they enhances the volatilization of the contaminants in the aquifers, and through that vapor will be more and more vapor will be produced, and it can be extracted and treated. So in bioventing, oxygen along with some other nutrients are supplied into the aquifers to enhance the microbial activity or microbial degradation taking place in the aquifer, which convert the pollutants more into the vapor phase. And in heat treatment, the temperature is increased, which volatilizes more and more contaminants into the vapor phase. And through these two methods, the solid vapor extraction process can be enhanced. So A is the correct answer. That statement is true. Am I audible now? So can any one of you can confirm whether I'm audible or not? So A and C are the correct answer. So this site was contaminated with various chlorinated organic compounds like TC and DC, and also it was contaminated with hexavalent chromium and cadmium and manganese. So the site was polluted with TC, DC, VC, and hexavalent chromium. So this option is correct. And option A, that molasses was utilized as an electron donor, not an electron acceptor. So this is also correct, that molasses was used as the electron donor addition, because these are the organic compounds which can get it can get oxidized and it can donate electrons. So A is the correct answer. So option B, that a consistent decrease in DC concentration was observed throughout the remediation, is not correct, because the decrease in DC was not consistent. And the third option, that so DC initially increased from 7 to 100 micrograms per liter, and after 10 months of treatment, and then it decreased to 19 micrograms per liter. So DC concentration increase in DC concentration was observed, because TC, that is trichloroethane, it was getting dechlorinated from trichloro to dichloro. That's why the concentration of DC was increasing. And after 10 months, the concentration of DC also increased, because further dechlorination of the DC was taking place, and then the decrease was seen. So a consistent decrease in DC was not observed, rather initial increase in DC was observed in the initial months, and then the decrease in DC was seen. So the option third, that the site was polluted with TC, DC, VC, and hexavalent chromium, this statement is correct. And the last option, that post molasses injection reducing conditions, not oxidizing, were predominant at the site, this statement is not correct. The conditions were oxidizing, not reducing. So based on all these, option A and C are the correct answer. So I hope the screen is visible now. So now can any one of you confirm whether the screen is visible or not?
Yes, ma'am. Screen is visible, ma'am.
Okay, I'm so sorry for the delay, because I was not noticing a huge lag between the audio and the video. So question number 4 is, what is a key challenge in remediating heavy metals contaminants in soil? Option A is their high volatility. B is their tendency to biodegrade. C, their persistence, mobility, and their presence in different phases such as solid and liquid, such as in form of metal complexes. Or D, their attraction to organic matter. So we have to tell what is the challenge in remediating the sites contaminated with heavy metals. So like previous question, more than one option can be correct for this question and also for the following questions. So I will give you all 3 minutes. Just take your time and write the option in the chat box, and then we will discuss. So the correct answer is C. So, the first option that they're high volatility, so metals are non-volatile, below 500 to 600 degrees centigrade. So they are non-volatile. So their tendency to biodegrade. So metals do not degrade very easily. And also these heavy metals, some of the heavy metals like chromium 3, they are micronutrients. So their requirement for microbes is very, very less. So that's why they do not biodegrade also. So B is also not correct. So the last option C, that their persistence, mobility, and their presence in different phases, such as solid, liquid, such as in the form of metal complexes, this statement is correct. So when any metal, when any aquifer gets contaminated with these metals, so these metals can dissolve and they can be in equilibrium with the dissolved phase, and also they can get soaked into the soil particles, and also in the dissolved form they can form various complexes with different ligands present in the water. So suppose if their water has hydroxide, so they will form different hydroxide complexes. So if there is a chloride, then these contaminated metals can form different chloride complexes. So the overall complexity increases when there are different more and more number of ligands present into the groundwater. So option C is correct. And the last option, that their attraction to organic matter. So the attraction of metals to organic matter is not that much. So option D is also not correct. So C, that their persistence, mobility, and their presence in different phases such as solid and liquid, and in liquid such as in the form of metal complexes. So this contribute to the difficulty in remediating the soil contaminated with heavy metals. So C is the correct answer. So now let's move to the next question. So question number 5 is, which of the following is a common use of permeable reactive barriers? A. To degrade the contaminants as the plume passes through the permeable barrier. B. To aerate the contaminated zone. C. To absorb solar radiation. Or D. To increase soil temperature. So we on the basis on this question is based on PRBs, that is permeable reactive barrier. So we have to say out of the four options what is the most common use of PRBs. So again I'll give you all 3 minutes. Just take your time and write the option in the chat box and then we will discuss. So option A is the correct answer, that PRBs are used to degrade the contaminants as the plume passes through the permeable barrier. So option B, C and D, that PRBs are used to aerate the contaminated zone and to absorb solar radiation and to increase the soil temperature. So these three statements are not correct. So in PRBs, what happened? There are some zero valent iron or other compounds which helps to absorb or oxidize or reduce uh, or to absorb the contaminants while the plume is passing through the PRBs. So A is the correct answer. So now let's move to the next question. That is question number 6. So question 6 is, what role do phytoremediation plants plays in soil remediation? So first option is they physically break down contaminants. They stabilize soil to prevent erosion. C. They absorb and accumulate contaminants and degrade in the root zone or rhizosphere. Or D. They increase soil aeration. So, what is the role of phytoremediation plants in soil remediation? We have to select the or tick the correct options. So, again, I'll give you all 3 minutes. Just write the option in the chat box and then we will discuss. So the correct answer for question number 6 is C, that the plants absorb and accumulate contaminants or degrade in the root zone or rhizosphere. So they physically break down contaminants. This is not correct. Uh, and next is they stabilize soil to prevent erosion. So this is correct that they stabilize soil to prevent erosion, but not the statement is not relevant with respect to soil remediation. And option C, that they absorb and accumulate contaminants or degrade in the root zone or rhizosphere, is correct. So in phytoremediation, what happens? The plant takes the contaminants while taking the nutrients, major and micronutrients from the soil. They take the contaminants like heavy metals, and these contaminants are stored in the tissues of cells and tissues of the plant, and through this the accumulation of the contaminants takes place. And also there are a lot of microbes present in the roots of the plants which help in while taking, which helps in various purposes, like they help in taking the nutrients from the soil, and also they help in fighting or uh, uh, tolerating stress conditions like a very high concentration of heavy metals in the soil. So through these microbes, the contaminant degradation of the contaminants also takes place during phytoremediation. And option C, that they increase soil aeration. So this is not correct. So only option B is correct. So soil aeration is enhanced by insects like earthworm, where they dug the soil and creates hole in the soil, which increases the aeration. So now let's move to the next question. So this is a numerical type question. So the question is, a PVC factory has been contaminated by vinyl chloride and the remediation proposed is soil vapor extraction. So the following data is provided from field test. So the distance, the vacuum pressure with respect to distance from the extraction well is given, and also the flow rate is given as 0.01 meter cube per second. And the further statements are given are that the contaminated site has an average gas concentration is given, and some of the physical characteristics of site is given, like Weddow's zone thickness is given, volume of the soil is given, total gas porosity, total liquid porosity, bulk dry density of the soil is given, fraction of organic matter, and dimensionless Henry's constant is given, and partitioning coefficient is also given. So we have to assume that there is no NaPl is present. The mass of contaminants to be removed in kg is, so we have to round to 2 decimal places. So I'll give you all 5 minutes. Please try to solve this question, and then we will discuss how to solve this. So let me bring the table here. So this is the overall question. So we have vacuum with respect to distance is given, and the physical characteristics of the site is given, and we have to find out the total mass of contaminant to be removed when there is no NaPl. So I'll give you all 5 minutes. Please try to solve this question, and then we will discuss. So let's see how to solve this question. So first, let's write everything which is given. So it is given that volume of the soil is, or so the volume of contaminated soil is 2000 meter cube. Henry's constant H is given as 0.196. So it is dimensionless. So it is the ratio of concentration in the gaseous phase to that in the aqueous phase. So the partitioning coefficient Kp is given as 0.8. So it is given as 0.8 liter per kg. Next, the concentration of the contaminant is in gas phase is given as concentration of the contaminant in gas phase is given as 40 gram per meter cube. Porosity of water is given. Total water porosity is given. Liquid porosity is 0.92. Sorry, 0.092. Gas porosity is given as 0.3, and the bulk density of soil is given as 1650 kg per meter cube. So we can convert it into kg per liter. So it will be 1.65 kg per liter. So when there will be no NaPl, so the expression used to find out the total mass of the contaminant is so it can be written as mass in liquid phase plus mass with soil phase or sediment phase and the mass associated in the gas phase. So by arranging all the expressions, the final expression will be VCG, porosity of water by Henry's constant plus bulk density into partitioning coefficient by Henry's constant plus porosity of gas. So this expression was derived into in the lecture video. So please go through the derivation of this expression there. And finally, we have to put all the values, and we can, by solving this, we can get the total mass of the contaminant. So let's put everything here. So volume is 2000 meter cube. The concentration in gaseous phase is 40 gram per meter cube. Water porosity is 0.092. Dimensionless Henry's constant is given as 0.196. Bulk density is 1.65. Partition coefficient is 0.8 divided by Henry's constant plus porosity of the gaseous phase. So gas porosity is 0.3. So after solving this, we can get the final value. Let me solve this. So after solving this, we are getting 600,326.53 gram. So this is the final value, but I think we have to find the contaminant concentration in kg. So this is meter cube and this is gram per meter cube. So final expression we will get is in grams. So to convert it into kg, so we will divide by 1000. So it is coming out to be 6.33 kg. So this is the total concentration of the total mass of the contaminant when there is no NaPl phase present in the aquifer. So now let's move to the next question. So if you have any doubt, then you can ask, or if there is no doubt, then we'll move to the next question. Okay. Okay, let's move to the next question. So this is a similar question which was discussed in the lecture video. So the question is the average concentration of the contaminant is 1.42 gram per meter cube. Assume that the average concentration extracted is 10% of the initial average, and then calculate the time required to remediate the site. The average flow rate is 0.01 meter cube per second, and the total mass of contaminant is 1100 kg. So we have to find out the time required to remediate the site. So let me write the expression. So the time required to remediate the site can be given as total mass of the contaminant divided by average flow rate into average concentration. So please try to put the values in this equation and try to solve the question and write the value which we are getting in the chat box. So let's see what is the correct answer. So the time required to remediate the site. So it will be the total mass of the contaminant is 1100 into 10 raised per 3 grams divided by flow rate is 0.01 meter cube per second, and average concentration of the contaminant is gram 1.42 gram per. So 10% of the, actually the statement in the question is not correct. So the average concentration of the contaminant, this has already been calculated by considering that 10% has already been extracted, because because we are using C average. This is not the absolute value. So this is the C average which has already considered that the 10% has been already extracted. So this C average is the 10% of C naught, which is coming out to be 1.42 gram per meter cube. So the statement is slightly wrong. So this should be the correct statement. So anyways, so the total time that will be required to remediate the site will be 896 days. So it will be more than 2 years. So it's coming out to be 2.45. So this much time will be required to remediate the site. So I hope the question. Hmm, So we are getting 896. So there was slight mistake in the statement itself, that this average concentration has been calculated by considering that 10% is already extracted, and by using this we can find out the time that will be required to remediate the site, which is coming out to be 896 days. So let's move to question number 1, 2, and 3, because there was lot of lag between the audio and the screen. Yes, 7.75 into 10 raised per 7 seconds. This is the correct answer. So the first question was, bioventing and heat treatment are the methods which are used for enhancing soil vapor extraction process. We have to say whether the statement is correct or not. So in bioventing, oxygen, which act as an electron acceptor, and also some nutrients can be supplied into the aquifers, and through this, the degradation or the bioremediation of the soil of the contaminant will increase, because the activity of the microbes will increase, because they have an electron acceptor as oxygen, and oxygen gives very high energy, so the activity of the microbes will be very high, and the contaminants can be easily converted from the solid or aqueous phase to the vapor phase by the microbes. So bioventing is a method which enhances the SVE process. And the second method, which is the heat treatment. So with increase in the temperature, we know that the volatilization of the contaminants or any compound increases. So heat treatment will volatilize more and more contaminants. So more and more contaminants will be removed from the aquifer, so it will also enhance the SVE process. So that's why this is the correct statement. So A is the correct option. So next question is, consider the AFCO Lycoming Superfund site remediation case study. And based on that case study, we have to see which of the following statements are accurate about the methods and outcomes of the remediation process at this site. So four options are given. First option is molasses was utilized as an electron donor, not an electron acceptor. Second option is a consistent decrease in DC concentration was observed throughout the remediation. Third option is the site was polluted with TC, DC, VC, and hexavalent chromium. And the last option is post molasses injection, reducing conditions not oxidizing were predominant at the site. So based on this case study, we got to know that molasses was used as an electron donor because it is an organic compound. It can easily oxidize and can give electrons. So that's why it was used as an electron donor. And the second option, that it is a consistent, there was a consistent decrease in DC concentration throughout the remediation. This statement is not correct because in the case study we have seen that TC was getting degraded to DC, and that's why in the initial 10 months there was increase in the DC concentration, which confirms the conversion of TC to DC, and after 10 months there was a decrease in the DC concentration. So option B is not correct, that there was consistent decrease in DC. Rather, there was initial increase in DC in the initial months and then decrease in DC was observed. And option C, that site was polluted with TC, DC, VC and hexavalent chromium. This statement is correct because that site was contaminated with chlorinated organic compounds, hexavalent chromium, and also cadmium was there in the site. So C is correct. And the last option, that post molasses injection reducing conditions were predominant at the site. So this statement is not correct. So after the injection, oxidizing conditions were predominant at the site. So only option A and C are the correct options. So I hope this question is clear. Now let's move to the next question. So question number 3 is, land farming, which is an ex situ remediation method used to remove the contaminant from the soil, requires an impervious layer between land and contaminated soil to prevent leaching. So we have to say whether this statement is correct or not with respect to land farming. So in land farming, what happens? It is an ex situ remediation. In this, the contaminated soil is spread into thin layers onto the ground surface, and these thin layers can be aerated periodically to increase the amount of oxygen into these soil layers. With more and more oxygen going in these soil layers, the remediation or bioremediation will enhance because oxygen acts as electron acceptors. So more energy will be released, and these microbes activity can increase, and through this the remediation can be enhanced. So also, since these in land farming, these contaminated soils are spread onto the ground surface. So before spreading these contaminated soil, some impervious sheets or some impervious layers are spread before spreading the contaminated soil. So that's why the statement that land farming requires an impervious layer between land and contaminated soil to prevent leaching is correct, because if impervious layer will not be present, then if there will be rain, then leachate will be produced, and these leachate, they can go and contaminate the groundwater and the aquifer. So we need some impervious layer so that during remediation, the whatever contaminants that leach out, they will not go and contaminate further the groundwater and the underground aquifers. So this statement is also correct, that we require some impervious layer between the land and the contaminated soil to prevent leaching. So this statement is also correct. So next, okay, so from question number 4, we have started by, so I have started in the second half when where everything was sorted out. So these 7 questions were based on week 11 material. So